introduction. Indeed, we have been friends for a long time. Other people in Cergy, it's really a pleasure for me to be here. I believe my third ever international talk, outside Switzerland. There was in Cergy, so very early in my career, I gave a talk here. And yeah, you mentioned Utopia. We have a representative from Göteborg.
Yes,
from the north. So I would like you to discuss, briefly about the magnetism and some mathematics around it. So I'm going to retrace some of the aspects. Magnetism is a hugely complicated and very diverse topic, and I cannot touch everything. But I'm going to give a few points, and hopefully everybody can take something out of it. Not everything will be technical. So I'll start with some very brief history of magnetism. Then there will be the question of where magnetism comes from, how to explain it. Then I will retrace some of the history towards understanding what we can call the microscopic constituents, or nanoscopic world. Then there will be the question of describing large systems, and then there is some thermodynamics, statistical physics. And then I will come to the description of the subsystems, how we simplify things considerably. And I'll explain a little bit about the Ising model, which is a very simple system, but turns out to have very interesting mathematics. In one dimension, it's quite easy to understand. In two dimensions, that's the topic of my talk. And indeed, because I am with my grad student from Warwick, Georgios Athanasopoulos, we made some progress with the triangle lattice towards a rigorous proof of the exact formula. So this is the plan of my talk. Feel free to ask questions whenever you have some. So it starts with Greek and ancient Greece. So perhaps you can read these few letters of Greek. Mathematicians or physicists should, although we are not used to read it. But it's
there is a small error, but I explain it.
It's not correct.
No, the sigma is not the termination because of the sigma. The end of the word is not the same, but it's okay. There is nothing.
Okay. I have to apologize. This is my very first time. I'm already corrected. I might have made it. All right. So magnetic lithos, that is what I lithos, or magnetic stone. So this is something, a mineral which is naturally occurring, but the most common ore for iron, also called the magnetite. So magnetite is formed by iron and hydrogen. And this magnetite is naturally magnetized. So here you have a sample which attracts a lot of needles of iron. And so the presence of magnetic materials was first mentioned by Thales of Miletus, as you see, quite a long time ago in ancient Greece. There is a mention of magnetic materials in a Chinese text, also very early, in the 4th century before Christ. There is another mention in another great civilization, the Indian civilization, in a medical text. And it's interesting because not only it's mentioned that there are interesting properties, but they found an application. Namely, apparently you can use magnetic stones to try to remove needles coming from arrows in human bodies. So apparently they found medical applications. And this is in this very ancient text, which was written over several centuries, but it was definitely completed before the 3rd century after Christ. Then a little bit more modern, in the 11th century, Shen Kuo writes about the magnetic needle used as a compass. So that's another huge progress towards understanding magnetism, the relation with compasses, and the fact that it's possible to always to know the direction to the south. Apparently, the Chinese were always designating compasses so that they would point to the southern direction. And then in 1269, there is a first treaty on magnet by Pierre de Maricourt. The magnets also described by the Yemeni scientist Al-Ashraf Umar. I mean, it's interesting to see really, but that's something which fascinated everybody in the world. In 1600, the treaty by William Gilbert, and he was the first to understand that the Earth is a gigantic magnet, which is the one which orients the compasses. Because before that, people were not quite sure, and there were suggestions that perhaps the Polaris, the star of Polaris, I mean the northern star, is the one which is kind of attracting compasses. I mean, nowadays it seems kind of ludicrous. The star is very distant and not very remarkable, except for its location. But at the time, people really believed that there must be something. And also, there was a suggestion that perhaps there is a giant magnetic island in the North Pole. But so William Gilbert understood that there was something really with the Earth itself. And indeed, that's some of the core of the Earth. 1819, the first understanding that magnetism has something to do with electricity. At the time, I mean, electricity was a strange phenomenon, magnetism was another strange phenomenon, and there was no obvious relations between the two. And then more modern studies, sorry, I lost the connection here. I don't know what's the problem. Okay, it's back. So then, very important work by very famous scientists, Ampere, Gauss, Biot-Savart, Faraday, Maxwell, and many others. I'm not going to detail that. So now let me discuss a little bit of the history towards understanding what is the cause of magnetism. I mean, I have to tell you right now that magnetism is still very far from being understood, but still there are some understanding, I mean, some knowledge towards this. So perhaps let's meet first with John Dalton. It's John, not a Joe, I mean the French. John Dalton, but this one is John Dalton. So what's your name? Ignite seems to be the connection. Sorry, but I'm losing. I think you have your own, that should work. It's very stable. I don't know whether it helps if maybe Jakob, occasionally you can try to touch the screen and maybe I'm sorry about that. So John Dalton was very important in understanding the notion of atoms. I mean, now we are retracing some steps towards the history of atoms. Atoms were apparently the possibility of atoms was mentioned also in ancient Greece, I think. But there is still the question of whether there is any kind of evidence towards this. And John Dalton was the first to really look at certain chemical reactions, certain physical phenomena, and find that indeed the hypothesis of atoms makes them, I mean, allows you to explain them. He's also very famous, I mean, Daltonians is named after him, so for his studies of the color blindness. Then you have, I have to say the name in full because it's funny, Lorenzo Romano, Amedeo Carlo Avogadro, Di Parenia, Edi Ceretto. And he proposes this amazing ideal gas law, namely that the volume of the gas of particles is proportional to just the number of total number of particles in the system. And then there is this Avogadro's number, which is a very large number. I think it's not related to the name of the person, but the fact that there are lots of atoms. Then the botanist Robert Brown, who observes the motion of grains of pollen, and he is famous for two reasons, I would say. He understood what is now known as Brownian motion, which is very important in mathematics and physics and science. But he realized that it's so on the one hand, there is this notion of Brownian motion, which is a trajectory which is continuous but very irregular. But then he also understood that the reason why these light grains of pollens were making this erratic motion is because they were constantly hit by tiny invisible particles with the atoms. So it's in a way a possibility of directly observing the fact that atoms are present. You cannot see the atoms directly, but you can see that they immediately change the direction of these grains of pollen. So this was also a very important observation towards understanding that atoms are there. So I haven't quite understood what's wrong with because that's the connecting, so I can see it. So if it's the connection, or it's not a screensaver or something like that.
Wi-Fi? It's not a constant.
Yeah, right.
Or we could use a LAN cable.
Well, that's usually not the,
It's better. Maybe the connection.
yes,
Network.
yeah.
And quickly document the cable.
Again,
It's still trying to connect.
yeah, it's much better because the Wi-Fi does not change.
Si, Karine est connectée dessus.
No, it's back.
But yes,
Just have a share again.
they promise to upgrade our connection, but
That's a big issue for the university, the Wi-Fi doesn't work too well.
yes, really, it's a big problem for the whole university, it's not only local. Yeah, okay, and then, okay, I will come back.
So it's really the connection which is but should I continue or?
Yeah.
Yeah.
It's all right. Okay. we got
Okay.
it.
So the page before was towards understanding that indeed most matter is formed of atoms. Now the question is what is an atom? What is the atom made of? And here you have a list of people. So there is Johnson, for instance. He discovered that there are electrons. So atoms have electrons. And he could also measure the charge to mass ratio of electrons. Rutherford was the first to see that the atoms consist of a nucleus and the electrons around, and that the nucleus is very small compared to the electrons. And Chadwick discovered the neutrons, which are one of the two particles with the protons making up the nucleus. And then Niels Bohr proposed later his planetary model for atoms, so that the atoms are a bit like the sun with the planets around, but you have a nucleus with the electrons more or less orbiting around. So it's now, yes?
I'm a little bit lost in the figures. So the Brownian motion, could you just tell me how the Brownian motion fits into this whole? atom theory and?
Well, this page was about understanding that they are atoms, and the Brownian motion is so you see the grains of pollen, and the grain of pollen have this erratic behavior. So they are because they are in water, I think, and the reason is that they keep being hit by the particles of water, by the molecules of water. So if everything was kind of smooth, if it was a smooth liquid, you would expect the trajectory to be smooth. But the fact that you have these sudden changes suggests that you have these tiny particles and they keep hitting the grain of pollen. And most particles are quite light, but the grain of pollen is also light. So it's still enough to see that you have these changes, instant changes in all directions. But of course, most discoveries about the nature of atoms use more physical experiments involving a lot of radiations. So the discovery of radiation, which allowed to understanding a lot of things in physics, and especially the nature of the atoms. So then we come to Niels Bohr and the notion of quantum theory. But it was really a bunch of rules which were not very precise. In 1927, following the work of Schrödinger, but also of Heisenberg, there is a very precise law of motions for quantum particles. So this is really the birth of a new theory of quantum mechanics based on very precise notions. So here, just for those who are a little bit mathematically inclined, you have a notion of wave functions, which is an L2 function, integrable function. And the function represents the probability of finding the particle at a given site. Should take the modulus to the square. Then there is a Hamiltonian operator, which is an operator acting on functions, which describes the energy of the system, and it plays a role in the so-called Schrödinger equation. So here, just to explain a little bit, the structure of this thing is that psi of t is the state of the system at time t. This symbol means the derivative, so this is how the system changes all the time. And this changes according to this rule. So you take the state of the system, act with this Hamiltonian, it gives you another function, and it gives you the change. And from this, you can infer the existence of an evolution.
So when you say wave function, it means wave of probability that particle exists a certain.
So here it means function in the sense that it's a function of the space and time. So if you specify the location and the time, you get a complex number. So mathematically, it's this, but with some properties. So, but just to point out that by the time we reach Schrödinger's equation, quantum mechanics is set on a firm mathematical footing. Now we are really dealing with mathematical objects and an equation for its evolution. Now we want to understand magnetism, so there will be something to do with the quantum systems, but there is also something to do with large systems. So now I'm going to have one slide on one of the most curious theory of physics, which is thermodynamics. The origins go back to pressure cookers, and I'm really not kidding, and steam engines. So these things which look like they're very crude, and okay, you take water and you heat it up, but then it turns out that there were lots of questions which could be asked, and actually very interesting physics to be made. So here you have a list of major contributors, including Papin, famous for Papin, for the pressure cooker of Papin, Carnot, Kelvin, Clausius, Maxwell, and many others are not listed here. So the question behind the Industrial Revolution and the use of steam engines is how you can transform Energy, again, sorry.
So maybe you try to make
I said that this one doesn't work. I believe this, the electricity that should be. And then,
Yeah.
next problem is that,
Correct. You know, it's better.
right,
Yes.
problem is that the computer is heating up a lot, so I'm not sure that that should last long. Ah, right, let's do that.
No, it doesn't work. It doesn't work with the screen.
Ah, so now we are going to be in trouble. And the outlet is working because
Yes, it's working.
I'm getting less and less electricity.
Du coup, vous avez branché votre laptop. Ok. Vous avez Internet avec le câble ou pas?
Alors là, avec le câble, je crois, oui.
Ouais.
Parce que, ouais.
Donc, du coup, normalement, ça devrait plus faire de déconnexion, normalement.
Ouais.
J'espère.
Le problème, c'est que pas. Je n'ai que
La
trois
batterie est
qui
presque
fonctionnent,
vide.
c'est-
Ah oui, on
La
est
batterie est
pas.
presque vide, tu vois.
Ouais, la batterie, elle est presque plate.
Ah, d'accord, ok.
Et puis le quatrième ne fonctionne pas, donc je n'ai besoin d'autre pour la. Ah, ce que je peux faire, c'est se connecter
Tu
avec.
peux partager
Ouais.
la tablette via par Wi-Fi. Hein. Tu dois être sur le même. Non, non, il est en même problème parce que.
Peut-être HDMI, si on met HDMI,
It try to. No. So I can try to
Tu
connect,
peux essayer de partager avec
tablet.
AirPlay, quelque chose comme ça. Si tu cliques encore une fois sur partager, ça ne marche pas avec. Clique encore une fois sur. Et là, tu partages avec AirPlay.
Yeah, exactly. So but normally should
Sur la tablette.
I have to remember right. Spinning right, yeah. But you should tell me which one to choose and what
Magnetism, Ueltschi, Magnetism.
No. Ah, right. If I put it back.
Tu vas partager la connexion. Non, c'est pas.
Merci.
Tu peux partager la connexion Internet de ton ordinateur avec.
Yeah, but I can see here, it is asking for the connection, and if it's play, unable. Yes, I guess we can. I don't know what we were name. Something to disconnect here, I guess.
Yeah.
Stop share.
Yes, it's in the corner. Yeah.
Yeah, I got it. Oh, yeah, that's sound but here, I guess.
Yeah, good.
And now you can try to share. And yeah, and now you need to put this here. I trust it. Yeah, go to I think.
No, it's not. Hmm? That's not. Yeah, it's a question. The magnetism, there are some magnetism on the screen. Some magnetism.
Now I need to blend the device.
The jack is coming, so.
If your passport.
Oh, fine.
Direction is missing.
Quelque chose.
The reference is really feel right.
Mhm. Or we can also try to use a USB. Il peut pas reconnaître. L'ordinateur qui.
I can share my Unreal connection with your PC if you want. So you will have a good signal.
Ah, so ok, on va faire comme ça. Yes. All right, so back to thermodynamics. So indeed, it started in the Industrial Revolution, and that's where people were understanding the possibility of getting energy out of steam engines and out of steam. And then there were all sorts of questions, because in a steam engine, basically, you start with a fire, so you bring heat to the system, but you'd like to extract work. And heat and work are expected to be both aspects of energy, but there is a question of how to transform heat into work, and conversely perhaps. And there are lots of restrictions how you can do it. And the restrictions will not only engineering, so because of devices, but there were some fundamental reasons why certain transformations were allowed and some were not. So the very new concept that started with thermodynamics is the concept of entropy. And this allows to understand lots of things. So for instance, you can define the notion of temperature. Temperature is something very common. The official definition, I mean, the scientific definition is as the derivative of the energy with respect to the entropy. So the existence of entropy makes it possible to understand what temperature is. So we said thermodynamics. Thermodynamics dealt with things like water or steam without actually making reference to whether the water is made out of atoms or anything. But at the same time, we know that we have the microscopic laws, I mean, quantum mechanics, to control the behavior of the systems. So the natural question was how to reconcile the two approaches, one macroscopic from thermodynamics and one microscopic using the microscopic laws of motions. And the person who really understood first how to understand thermodynamics out of the microscopic laws was Boltzmann. And he got this notion of Boltzmann entropy. So here you have, I mean, if you go to Vienna, they have a cemetery with lots of famous people, and including the tomb of Boltzmann. And if you look a little bit closer, here you have an equation, which is indeed S for the entropy is K, which is Boltzmann constant, times the log of W. W is probably something for Val. Andreas can check this, which is counting. So you count how many states are at disposal, and you take the logarithm, and it gives you a notion of entropy. So it's in something very simple, but it's actually very deep and very far-reaching. So the notion of Boltzmann entropy, then major contributions by Gibbs and Maxwell. And indeed, for instance, another way to go from the microscopic to the macroscopic is through the free energy, which in thermodynamics is the energy of the system minus temperature times the entropy. And it's an important expression for thermodynamics, and it turns out that one can write a microscopic description equivalent to the Boltzmann entropy. So this is what we are going to do with Ising models shortly. But now let me go back to the question of describing this microscopic system. So in principle, we have all the things we need. We have the laws of thermodynamics. We have statistical mechanics, which allows to go from one to the other. So we can define things, but it's very complicated to actually get anything out of these systems. So what the people are doing is to introduce the notion of models, where we simplify considerably the situation we are dealing with. So among the many simplifications, we are going to decide that atoms are fixed particles. So we are dealing with atoms and with electrons, or I mean, I should say nuclei, so the fixed are fixed particles, and the electrons will be the ones that we are going to try to understand the behavior. Many electrons are tightly bound to atoms, so only a few electrons are going to matter, and the others we kind of assume they are glued to the respective nuclei. And the electrons move on the sides of the lattice instead of moving in the continuous space. So if you do all those so-called tight binding approximations, you get something called the Hubble model, which is a more simplified model, so-called lattice model, which turns out to be still extremely complicated to study. I mean, if you want to hear more about it, you can ask Andreas. No, that very about it. There are further simplifications. Instead of having all these quantum electrons carrying spins going around, one can restrict only on the spins of the electrons, because each electron carries a spin, I forgot to say, which is a little magnetic moment. And one gets a simpler model called the Heisenberg model, still very complicated. Yes?
A quick clarification, when you say statistical mechanics, that's quantum mechanics. Or is that
No, it's another branch of physics which deals precisely with a large number of particles. So now it can be based on which microscopic laws govern the particles. So statistical mechanics applies to classical systems and to quantum systems, to be clear. So to both. And so we have the Heisenberg model with these little magnets, but these are still quantum spins at every side of the system. If one if one replaces by these quantum systems, quantum magnets by classical spins, we get the Ising model. So the Ising model is something very simple. So it was introduced by Wilhelm Lenz in 1920, studied by his PhD student Ernst Ising in 1925. For some reason, it's called the Ising model, even though, it's actually, usually the credit goes to the more senior person, irrespective of the work. Here, curiously enough, the credit went to Ising, even though Lenz arguably was the person really behind good ideas. So it's a very simple model. So here you have a two-dimensional lattice, a square lattice. At every side, you have a little magnet, which is a little arrow, either pointing up or down. That's a major restriction. We just have those two directions. And another way to describe such a configuration, so these little arrows, is to say that every side you have either a +1 or -1. So this is the configurations of Ising. We have all those sides spaced regularly. And at every side, we have a +1 and -1. And the spin configuration is random. But at the same time, there will be a distributions which depends on the temperature. Temperature is going to be a parameter. And at high temperatures, all those little spins up and down independently. While at low temperatures, there will be, the measure will be so that the spins will be encouraged to actually be aligned, with the neighbors. So what happens is that at high temperatures, those spins are essentially independent. So if you look at the total magnetization, which is, you add all those little arrows, or you add all those +1 and -1, and the question is whether, in average, it's kind of zero, or whether you point, it's mainly all pluses or mainly all minuses. At high temperature, you have more or less an equal number of pluses and minuses. So the total, if you add all those, you get close to zero. While at low temperatures, they are going to be kind of forced to be aligned with the neighbors. And then there will be the possibility of propagating this local rule to a large scale, and to have an overall either pluses or either minuses. So that's somehow the intuition behind this. So I'm not going to write precisely the model, but I mentioned this thing that one can go from the microscopic to the macroscopic. And here is the major formula. So this is the formula for the free energy. So the free energy depends on two parameters: beta, which is the temperature, or actually the inverse temperature. That ought to be more convenient. And H is the external magnetic field. So then this free energy, which is the thing in thermodynamics, is given as follows. We take first, we are going to sum over all those configurations of spins. So for each side x, we have a plus and minus ones to sum up them. Everything is gets this weight over here, that's the exponential beta, and we take the sum over all neighbors and sigma x, sigma y, and plus h sum of sigma x. So for those who know a little bit more, this is minus the Hamiltonian of the configuration, minus the energy of the configurations, and we sum over all configurations, exponential minus beta h. That's again, that's a prescription. We take the logarithm, we divide by the volume, which is L to the D because we are in a box of size L, and we take the limit of larger and larger systems. So this, we get the number at the end, or I mean, for each beta and h, we get a number. And this gives the free energy of Ising. And now we can ask the questions about this function f. Is it smooth, or is it, I mean, what kind of function is it? The idea is that what you expect is that at high temperature, when you sum over all those configurations, the main contribution is when we have an equal number of pluses and minuses, roughly. But when we get to lower temperatures, there should be a dominant contributions of mainly pluses or mainly minuses. And then it's going to affect this function. And the fact that at some point we get these special properties should be reflected on the fact that this function f is not smooth anymore. So that's the idea. Anyway, the thing is that for all systems, we have here a well-defined formula. This makes sense. So this was established already in the 60s by mathematical physicists. This kind of limit completely makes sense. The question is to extract some properties of a system, and that's the difficulty to do. I mean, what can we do with this formula? It's a finite sum here for finite L, but it's a huge sum. I mean, the number of configurations is 2 to the number of sides. And if you know anything about exponentials, it grows extremely fast. So this sum is totally impossible to do by hand.
Can I ask you a really stupid question?
Yeah.
So half should increase in beta, right? Because beta is temperature.
Yes.
Right? So then the first term inside the exponential function, that's beta times sigma, and that as temperature goes up, they should cancel out with each other, and that converges to 0, right?
Well, I mean, depends on which configuration. So beta is the inverse temperature. So if beta, I mean, if in a high temperature, beta is small.
Reverse.
Yeah, it's the
Okay,
inverse.
one
It goes the
over
other way. So when you go to
Is it
infinite temperatures, beta goes to 0, and then you're going to just sum over this, and you get exponential 0, which is 1. When beta becomes large, it corresponds to low temperatures, and in fact, here you will get the dominant terms when more or less all of them have the same sign. I mean, it's quite clear, but you get some exponential. Exponential large term, and when you have an average of both, you are going to get much less. So this function indeed reflects, I mean, and this intuition of what are the most typical configurations is very important. I mean, it's very direct, but that's the reason why the function will have a certain shape.
So Daniel, related question. As a physicist, I would also write the beta in front of h. Is that a typo or is it intentional? So
It's intentional here, but you're completely right. There should be a beta here.
because otherwise the high temperature limit
That's
don't stay.
That's right. Yeah. It's just convenient mathematically, not to here. But you're completely right. There should be a parenthesis like that. And the H should also be multiplied by beta. So my H is like your beta H. and then the beta is not the inverse temperature, it's one of the KBT. The Boltzmann constant should be there, and also the everything else. I'm no longer a genuine physicist. No, what's mathematics. So Ising's contribution is to understand how to calculate this the formula before, but in one dimension only. And then I'm not going to explain it in details, but it turns out that everything can be written in terms of a 2x2 matrix. For those who know what the matrix is. So it's a 2x2 matrix indexed by sigma and sigma prime are plus and minus 1. So here you have like plus 1, minus 1. So the index set is not traditional, but otherwise it's really a 2x2 matrix. And it turns out that the free energy is the limit. 1 over L, so D is equal to 1. And then we have just the log, there should be also a minus 1 over beta. I'm sure Andreas is going to point out here. But then we just have the log, the trace of this matrix raised to the L, to the power L. And then, if you remember a little bit of algebra, this is something very easy to calculate because you can diagonalize this, or I mean, find the eigenvalues of this matrix. And then you immediately have the eigenvalues to raise to the L. Only the largest eigenvalue matters. It's very easy to identify. And then you get this formula over here. So it looks like a complicated formula, but it's kind of elementary. I mean, it has only elementary terms. I mean, a logarithm, it's a standard function, exponential, a cut, hyperbolic cosine. It's a bit like a cosine, but it's actually simpler than a cosine in many respects. And then a square root and something which are quite elementary. It's easy to check that such a function is very smooth in beta and H, called analytic. So nothing really interesting happens over here. And actually, that was the conclusion of Ising. He understood that this model is not really good for describing anything in one dimension. And he argued that in 2 dimensions, it's probably still the same. So, and that's where his study stopped. But it turned out that the 2-dimensional model is actually very interesting. The calculation is much, much more complicated. It's been done only for H equals 0. We have to mention here. So this is f of beta, and we have the H, but the H, the magnetic field is now set to 0. And then for this, as a function of beta, it's given by this. It looks complicated, but it's a much simpler formula than what we started from. I mean, we have this huge sum of all these plus 1 and minus 1s. Now we are left with only one double integral, I mean, k1 and k2 between minus pi and pi. And then with this function over here, log of the Cauchy square minus sinh and percent k1 percent k2. And this part over here is represent. I mean, what this picture represents is just this integral here. So first, I have to thank my student Georgios and Jakob for helping me getting those pictures. I mean, Jakob actually saved me this morning, 1 hour before the talk. I could put those pictures in the slides. And so the question is, how smooth is this function? Because we would like to say that when we vary beta, at some point we get to, from these high temperature situations where the plus and minus 1s, I mean, plus 1 and minus 1s are not too much correlated, to something where correlations occur. And so the question is this function smooth or not? And it's hard to I mean, it looks like very smooth, but let's look at, we're going to look at it a little bit more, and we'll see that actually it's not completely smooth. So it turns out that there is a critical temperature. To understand where it is, I mean, first let's see where it. So perhaps I should actually show you the functions first. So this is this double integral with a log and everything. Now let's look at the derivative of this function. If you remember what the derivative, so I mean, here you have a beta, here you have a function. The derivative means the slope. So now you can put the slope, and I mean, the slope here is very negative, so you take a very negative function here. The slope is less and less negative. Here it becomes positive, so when it crosses, then the slope is positive. And so this is the derivative of the function. So the function looks very smooth, but you see that this function is actually a bit less smooth. So there is something here occurring. Still, this function over here is a so-called C1 function, differentiable function. You can take the derivative, so look at the function made of its slopes, and you still get a continuous function. Let's take the derivative of this function here. So that's the second derivative over here. So we take the function of the slopes over here, and we get this. So you see, I mean, here you have a very positive slope, so you get high values. And when we get over here, we get this curious thing here. So this function clearly is no longer a smooth function. So one sees that the second derivative of the free energy has something interesting. So this is actually really remarkable. I mean, everything comes from this exact calculation, which was really an amazing tour de force of Onsager. So to understand this critical, I mean, we see that there is this value over here where something occurs. So to understand where something may occur, one has to look at this expression over here. We integrate, okay? And then we have a log of this thing. If you remember about the logarithm, it's a very smooth function, but not around zero. Log of zero is not defined. It's like minus infinity. And this can be delicate. So the question is whether when we look at, I mean, integrate over all those values, we have a cosine. Is it possible to approach zero? It turned out that this depends on beta. One can check that there is only one point where one can actually reach zero. We need for this to, but this, I mean, one has to take first K1 and K2 to be zero, so that we get +2 over here. That's the lowest possible value we can put over here. And then in this case, what we get is a cosh square minus 2 sinh square. And so, I mean, as it turns out, this is always positive or non-negative. But there is one possibility for beta where this is zero. And this, I mean, if you remember that the cosh square is like, I mean, cosh square minus sinh square equals +1. If you remember, cosine square plus sine square equals +1. The equivalent for the hyperbolic functions is cosh square minus sinh square equals +1. So we can replace this by sinh square minus 1. And we get this, or +1, and we get this equation over here. So forget that this is a sinh of 2 beta c. You have a number squared minus 2 times the number plus 1 equals 0. That's a perfect square. And we get 0 when the sinh is 2 beta c equals 1. So this gives us this very specific value for beta where something occurs. And one can check that this has also this function, this value here. So this is exactly this value. It turns out to be the minimal value here. It's a bit coincidental, but that's the value here where something bizarre happens, and definitely the value here where we can see that the second derivative behaves in a non-smooth way. So this shows that something happens there, and this is indeed the sign of the first transition. So otherwise, we can also look at the free energy as function of the magnetic field, and it's good to contrast the high temperature versus low temperature, and 1 dimension versus 2 dimensions. So here, these are just qualitative plots. I mean, in 1 dimension, the formula exists, mean, f of beta h, of beta n h. But what one gets is a concave function. It's symmetric for plus and minus h, and it's very smooth always. So this is for high temperature. For low temperature, where we expect something drastic happening because of this magnetic properties, still we get something a bit more peaked, but it's still very smooth. So in one dimension, both the function f of beta h is always smooth. While in two dimensions, at high temperature, you get something very similar. But for low temperature, what happens is that that's going to be this non-differentiable point here, gas. And so the function goes this way. So here one sees that there is something drastic happening to this function f of beta h. I have to say that, I mean, this function is known. That's coming from Ising, and you can, I mean, it's known for all beta and h. For the two-dimensional case, this function is not known. It's only known at h equals 0. But at the same time, qualitatively, we know that the plot is like that. And then there is a notion of spontaneous magnetization, because we can take those functions and again plot the derivative. So that's the derivative with respect to h. That's actually the magnetization. So when you have a smooth function like that, I mean, the derivative is that the slope is, I mean, it's minus the derivative. The slope is very positive here, so you get something very negative. And the slope is 0 here, so you see that we have reached point 0. And then things get more and more negative, which means higher and higher here. But the function is always something smooth like that. While if you take the derivative here, then when you go from this point to this point, you jump with the derivative. So this function is no longer continuous. And something which is absolutely remarkable is that the value of this point, which is, I mean, minus this point over here, is known. So it's another exact calculation, which goes back to Onsager, who actually proposed the formula, but did not write any details of the calculations. And it was only later the Nobel laureate Chen Yang who proposed the detailed calculations for how to get the formula. And the formula is here. So, I mean, it's something very explicit. It's absolutely remarkable that one can get it. It turns out to be a very important result in the theory of critical phenomena, because we can reach, I mean, we can calculate one critical exponent from this function. But, I mean, just the fact that such function exists is just more miracle. So briefly, I have another 2 minutes, or I need 2 minutes, I guess. So just to mention the possibility of defining the same model with these pluses and minus ones, I mean, minuses at every side, but on a triangular lattice. And it turns out to be interesting. I mean, it's a bit similar, but if you take the coupling constants, so I mean, so when we sum over, I mean, the energy of the system, when we sum over the sigma x, sigma y, we multiply by these constants, and then there is a constant for this direction, a constant for this direction, and a constant for this one. If those constants are negative, we get a so-called frustrated system, and it turns out to have different properties. So it's interesting to look also at the case where those numbers are negative. And then it's harder to establish the formula. But the formula was calculated by Ueltschi in 1950 already. So Onsager was 1944, so it did not take too long for people to master this and to extend. Also by Quetz and Stevenson. And here you have the formula. And I mean, just to mention a little bit my own work with my student Yorgos Athanasopoulos. So we have managed to apply the so-called Katz-Ward method, I mean, following Archin Lees, but also especially Michael Eisenman and Simone Barzel, to the triangular lattice, and find a way to make this rigorous, also in the case of negative couplings. So now I can just a few remarks to conclude. So magnetism is just fascinating physics, and it turns out one can really do far-reaching mathematics of the Ising model is very challenging despite the very simplicity of its setting. The exact formula by Onsager and for the square lattice, so that's the formula I presented. It's really something which is very unusual. It's only for the Ising model in 2 dimensions, but there has been these calculations which people could carry over. There are also interesting calculations about quantum systems in 1D, but somehow where the limits of the actual calculations are. It's really hard. Otherwise, we can extract lots of properties, but by computing direct means. And just to point out that the Ising model is very alive, and especially in mathematics, and it was, the work around the Ising model was recently recognized by the Field Medal Committee. Smirnov in 2010 and Dimitrov in 2022 got the Fields Medal for work directly connected with Ising model. I mean, they were not studying Ising model, but questions which could be illustrated with Ising model. So the story is not over yet. So many thanks for your patience.
Thank you, Valerie. Also, despite the 100 years after the discovery of the Ising model, the 3 dimensions is open.
Yeah, absolutely.
100 years to solve 1 and 2 dimensions.
So 5 years to solve 1 dimension, and then 24 years for 2.
Now,
3 years, still waiting for 3.
But now the Ising model is used for quantum annealers, right? So if I'm not wrong, the implementation of programs in quantum annealers are based on Ising models.
So this I don't know, but may well be.
These are based to programming for quantum annealers. Yeah, because in quantum computers you have the quantum gates, and there is also the quantum annealers where you have this energy equilibrium, and this is programmed using the Ising model. So you express a problem into as an Ising equation.
Okay, yeah. Okay, yet another directions for applications of Ising.
future for the next challenge. Yeah, so questions, comments?
So all this analysis, and I tried my best to follow, and so it could be applied to other forces as well, right? I mean, because all the forces are unified these days, of course, right? So magnetism and electronism is one thing, and now they combined all this with nuclear forces as well. So why magnetism stands out here? And just it is.
Well, but I mean, you have a search for fundamental laws of natures. This is one thing. Another question is actually to find what behavior emerged from the fact that you have many particles. So here the question is not, I mean, there is some relation with the fundamental laws of nature, but we really want to understand the properties of all those systems interacting. And here, I mean, you're completely right that there are always, the four forces. But on this level, it's kind of clear that only the Coulomb forces are important. So what we would like to understand are these nuclei, the electron treated quantum mechanically, and all the interactions are just the Coulomb forces. We can neglect gravitation. It's too weak for the scale at which we are interested. And we can also kind of neglect the other forces. I mean, they are the ones which make the nuclei stay together. But so we just accept that the nuclei are just staying together. So in fact, we know perfectly well how to write the descent model, which is the electrons treated quantum mechanically, and they all interact with Coulomb forces. But we cannot extract any useful property of that. So is there a phase transition in these systems? We don't know. It's just too complicated. So that's where those models came in. And that's really another kind of direction of physics. and that's the essence of statistical physics. Statistical physics does not care too much about the microscopic setting. It just assumes different microscopic settings, and the question is how to go from the microscopic to the macroscopic, and to get these things like magnetism, which is really a phenomenon which is due to the cooperations of all these little agents, these little spins. So even if one could understand the fundamental laws of nature, one would still not make any progress towards magnetism.
When you say macroscopic means thermodynamic domain.
Macroscopic means basically at whole scale, but and microscopic means on the level of the atoms. Very nanoscopic.
In the first slide, when you show a grid of the its values are between -1 and 1. No, the first one, there is a grid to show the very beginning. That one exactly. So it shows the speeds go from -1 to 1, and you said that at low temperatures, the neighbors kind of align with each other, and so it means that do you know what happens if you stimulate this kind of, I mean, I'm always looking for the computational point of view because I'm a computer science and neuroscientist, and I like computation with physical media. And so if you stimulate this kind of grids in different parts, so the kind of interactions that emerge, do you think that is do you have like I mean, for example, in a fluid system, you will have waves, or waves propagating, and the interaction between waves will create some interesting dynamics or interaction between them. In this system, will it be possible to observe this kind of interactions, or they will just tend to go all up or all down, depending on the
Yes, but for instance, you can simulate this. I mean, at high temperatures, the spins are typically
not aligned.
Not very much aligned. I mean, on a short scale, yes, but
okay, that's good. So
but only on short scales.
I see.
So at high temperatures, you don't expect much interesting stuff. But at low temperatures, you can ask a lot of interesting questions. So, for instance, you can also simulate this with a little magnetic field. But you start, for instance, from the minus phase, or a mixture of minuses and pluses. But the magnetic field is going to encourage to switch, but very slowly. So then you can have a front moving. You can also describe interfaces with this thing, and with interfaces, you can also look at what happens when you get to them, and perhaps you can have a wave-like behavior.
Okay. Interesting.
But otherwise, the Ising system is still a bit simple. Then you have variants of these models where these, for instance, classical systems where those little vectors are allowed to rotate, I mean, to point in any direction. And then spin waves are actually something which
could you recommend a simulator? Simulating.
Well, so for Ising, I mean, it's known that you have this Swenson-Wang algorithm, which has been very fast, and I think it hasn't been improved much since. Okay. So there are tricks. I mean, the Monte Carlo simulations work very well with Ising. So here you start with a configuration like that, and you propose to switch a spin, and you do it with a probability which depends on the neighbors. Basically, you're going you're tilted towards aligning with the neighbors, but with a certain speed. But at the same time, you have a possibility of not aligning. But then people have discovered these much faster algorithms involving different representations. Also, you have clusters, and then you can switch all the spins on the clusters, and that converges much faster than what's equilibrium. So there has been lots of simulations for Ising. Sure.
I would like to ask a more technical question. So on the triangle vectors, can you say a few words what is behind actually the computation? Is that transfer matrix, or how do you do this?
No, so we're using this Gatsword method as So this is a kind of a miraculous identity for which works for planar graph, involving the determinant of a certain matrix and a sum of the even subgraphs. And it means that, I mean, why sum of the even subgraphs? Because you have these high temperature representations for Ising, which is precisely some of the even subgraphs. And then, so you can, then this Katzwort thing allows to write a certain square root of a determinant as, I mean, okay, a sum of the closed loops, which cannot overlap, cannot share an edge, and which in fact can be connected with these even subgraphs. So there is a miraculous identity involving this Katz matrix or Katzwort matrix, which is something a bit indirect. I mean, the matrices are indexed by directed edges. That's already something not community standard. But this is the source of the identity. The problem, and I mean, once you have this, the temptations and what actually physicists used to do is to replace this matrix on a planar graph. So you have a large rectangle, but you replace it by a matrix which is translation invariant, and then you can diagonalize it using the Fourier transform. But to do this change, it's not clear that it's rigorously justified. So that's where the mathematicians are a bit annoyed. And recently there was this work by Ising and Barzel who they could really explain how to treat this change. And so they proposed an expansion which works for non-planar graphs, so like a torus, which is translation invariant. But then there is an extra complication. So it's okay, thank you.
Another really simple question. Sorry. So the free energy depends on the temperature and electromagnetic field. Right? Yeah. So yeah. But there are other, so like other forces like gravity. This is just because you can only just because it's too small compared to.
Yeah.
Okay.
So this is a free energy for Ising. But the idea is that things have been simplified a lot. But yeah, I mean, at this level, I mean, gravitation is just too weak. Now the nuclear forces are very important because they are the ones responsible for the existence of atoms. But apart from that, I mean, if you just accept that the nuclei are just point particles, very tight, and they just carry a charge, there is no need to describe, I mean, to use these forces anymore. So, and then Coulomb forces are really those. That's the force which is relevant here.
Questions or comments? But we can continue upstairs with the coffee. Thank you again. We'll talk about the technical issues. Hopefully next time everything will be fixed. The computer department or the communication department promised to fix everything. So where were you? Okay, so then go to the property upstairs and go. Give it to you for your upstairs.
Yeah, thanks.
Yeah. But by the way, in 2 weeks from now, the next guest lecture will be by a visitor from Illinois.